sure how it does. All right, next up we've got Tycho Anderson, who's going to be talking to us about an operator-centric way of updating application containers.
Maybe. Yeah, all right, cool. I can hear myself even. Hi, everyone. My name is Tycho Anderson. I work at Cisco on sort of a Linux/container platform. And what I'm going to talk to you about today are basically some ideas we have about how to do this better, how to do updates better. And in particular, a lot of this is a work in progress. So there's a slide at the end where it's like, here's some links to GitHub. Please come help. But I'll try and point out like what we're thinking about. And then I think the last thing I should say, my boss would be pissed if I flew all the way here and didn't say we're hiring. So we're hiring. Check. Just a little bit of history. So first, there were system containers. LXC used tarballs. OpenVZ had this runtime thing where you could do some fancy stuff with a thing called ploop, but it was mostly just a tarball, at least for image distribution. And building rootfs people generally found painful. There wasn't really a lot of tooling built around creating a rootfs. LXC runs them. OpenVZ would run them with this fancy ploop thing, but if you as a user wanted to create your own rootfs, it wasn't super easy. And then application containers came along, and there's kind of two application container formats which look mostly the same. And they sort of made building rootfs easy. And this is, people really liked Docker because it had the Docker file and you could install stuff in a nice way, and it would give you an image at the end, and that was very nice. And so that's sort of where we are today, is we have both the Docker and OCI formats, and people use them and they can build containers, and that's very nice. But we sort of have a problem about updating and just general management of these things, because tar is kind of an old format. And so anyway, just some basics before we move on, so that I can kind of start the problem. This is, I'm going to describe all of this in the OCI format, because that's the tooling that we've implemented is all has to do with the OCI format, but the Docker format, this is roughly the same. So anyway, what it looks like is there's an index which has say a list of manifests. All my things are off because I had to switch from 16 to 9 with 4 to 3. So anyway, the first OCI layout, if you imagine the error pointing from index.json to the bottom thing, it's basically what it is it's a content addressed hash of a JSON blob that describes information about the image. Then there's config, shift that in your mind up one. And the config describes properties about the image, like what environment variables to set, what the entry point is, things like that. And then there's the two layers, which are the actual bits on the disk in the container image. And in particular, each layer is a tar, or optionally a gzip compressed tar file. And the image is basically made up of these sets of manifests, config layers, these sorts of things. And so one of the drawbacks, actually, so there's basics and drawbacks, and one of the drawbacks is that it is indeed just a tar.gzip file. And one of the reasons is there's no deduplication. So the way these things are typically constructed, you build one layer at the bottom, and then you make some changes in the next layer. And for example, if you make a 1 byte change in a 1 gigabyte file, OCI or the tooling says, oh, this is different. I'll recompress this whole 1 gigabyte file. So for that 1 byte change, you basically end up with 2 gigabytes of data, where you really only need 1. So there's no deduplication like this at all of files, or even similar bits across different files. The whiteouts are kind of painful, so tar doesn't really have any concept of lower layers. So what happens is the OCI standard invents this thing that's called .wh.foo. And so if a file in one of the upper layers has a prefix that's named this, then during the extraction process, it deletes that file and anything underneath it if it's a directory, which is fine, but then you still have all that data in the lower layers, even though you're never going to use it. So this is, again, it's not deduplication, but it's, it's not awesome. So large layers are painful. So in particular, we have layers that are between 8 and 10 gigabytes, and gzip, you can compress it in parallel if you're clever, but you really can't decompress it in parallel. And so that means there's basically one core that has to decompress 8 gigabytes of data because it's just one big long tar file. And so that's not ideal. It can be slow. And turns out I'm not the only one who's observed this. And this is like a gigantic blog post that goes into lots of details about what else is wrong. These are sort of major drawbacks from my perspective, but there are others. And there's also a lot of history about how tar evolved to be the way it is, if you're interested in that sort of thing, like a lot of Unix spelunking and whatnot. So let's take a step back and think about what would actually be useful. So in particular, at Cisco, we're interested in image provenance. So basically, when the build system builds an image, it should sign that image. And then from then on, we can take the signature and validate it. And we can figure out, okay, this is really the image that the build server built. It's okay to run. Nothing bad has happened. We also want auditability. So basically, we want some way to say, the thing that's running on, like if we have a running machine with a bunch of containers deployed, we want to be able to ask that machine, are you running what was signed at build time? And there's a number of ways to implement that. I'll talk about it in a little bit. And the last thing is, or not the last thing, but one other thing is updatability. So, and this is sort of the work in progress part. We would like to be able to swap out some dependencies without actually having to go back to the developer and say, hey, can you rebuild us a new container because we need a new version because there's this CVE and libSSL or whatever. So we'd like to be able to swap out SSL, but still maintaining all of this other stuff. And then there's the last one is sort of use less space. So all the problems I was just talking about deduplication and all this stuff. If we have an image, we shouldn't be shipping around these bits in production that nobody's ever going to use. Yeah. So if we look at image provenance, basically you can, because of this clever thing, you only have to sign the index.json. You don't have to sign anything else. And the reason for that is all these layers and everything else is content addressed. So if the index.json has a SHA-256 hash of the content, if somebody changes a bit, all you have to do is go verify that the hash matches the file name, and if it doesn't, then things are bad and you can throw an error or whatever. So image provenance isn't really that hard, and sort of the image format design supports this very nicely. And for Auditability, you'd sort of like to be able to do the same thing because the image format could lend itself to this, except that you have to extract all these tar files. And so as soon as you write that onto a file system, you can't put the genie back in the bottle. And so what that means is there's no way to go from a file system that you've extracted back into the tar format so that you can check all of this stuff to make sure that the signature is valid. And even if you could, you would still have to keep another copy of the tar file around just to make sure that everything was there. So that's not awesome. So there is a way actually to do this that's supported in Linux in the kernel today, which is a feature called IMA or IMA, depending on who you ask. And it stands for Integrity Management Architecture. But what it really means is you can put a hash or a signature in the extended attribute of a file. And then at runtime, the kernel will look for this special extended attribute. and hash the whole file during the open call so that you can be sure that when the kernel hands you back a valid file descriptor that the hash is matched and none of the data has been tampered with. And that's very nice because tar supports extended attributes. So we could actually shoehorn use of IMA into the OCI image format without a lot of changes, and it would sort of just work as long as you distribute a policy, and there's a few other things, but for the most part you can put the metadata in the existing format. So yeah, the checksums are stored on, yes. So the question is why don't we just do this, because that seems easy. The first reason is because then you have to use it, and if you've ever dealt with this before, it's sort of painful. So the policy language is a little bit funky. They use a lot of very specific terminology that really is only specific to them. So the way they talk about key rings and all this sorts of thing is kind of different than the way everyone else in the whole world understands it. Also, it's really not necessary. So if we just sign that manifest, if we had a better design, we only need one signature. We already have the information we need. So we could do this for free. And given that the tar file isn't really ideal for this sort of thing anyway, if we're going to throw that away, maybe we can be more clever and get this for free. So we could use Squashfest instead of a tar file for this, and that sort of gets us most of the way there. So what is Squashfest? It's a mountable read-only file system, and in particular, if you read the kernel documentation, it says Squashfest is intended for general read-only file system use, for archival use, in particular in cases where a tar gzip file may be used. Okay, sounds good. Kernel developers wrote that. They're smart people. Maybe we should use that. So one of the advantages of Squashfest is that the metadata is stored separately. So if you know how a tar file works, it's basically just a concatenation of first there's a header, and then the header describes if there's going to be any data. There's the data, and then there's another header, and then there's more data. And so if you want to open the last file in a tar archive, you'd have to seek all the way through the whole thing. And then you'd figure out, okay, this is the file I want, and then you open it. And then if the next file that somebody tries to open is the second to last file, then you have to seek all the way again to the second to last file. You can imagine building some index, but these guys already did it. The metadata is stored separately with pointers into the various points where the file data is actually stored. So it's seekable. And the last thing is they support parallel compression. So this problem I described earlier about because it's one big thing, you have to decompress it all on one core. You don't have to do that with Squashfest. So what would this actually look like? So basically we just use a Squashfest file system instead of the tar blobs. And so then we can mount each layer as a Squashfest thing just directly out of the image. And then we can map the whole thing with an overlay FS. And thus we only have one copy of the data. It's seekable, it's fast. We can do the signature verification because the blobs aren't being extracted. They're put onto some file system or really mutated in any way. They're just mounted straight out of the image, and everyone's happy. Except there's some issues. One issue with overlay is that the way that you pass directories, the way that you describe, put the layers in this order, is with mount options. And mount options are currently limited to 4096 characters or one page. So I guess on ARM, probably this isn't a problem, but if you're on x86, this is a problem. And roughly what that means is you get about 55 layers. So if your container has more than 55 layers, this strategy won't work for you. And I say approximately because it depends on kind of what the path you're mounting at. Of course, if you're mounting at some very deep path, then you get a lot less. But if you're mounting at something reasonable, var lib, whatever, OCI something something. The math works out to be 55 layers roughly. So again, I don't know if anybody here has containers or images that they're building with more than 55 layers, but we have roughly 200. So we can work around this, but it's kind of a limitation. They also have a non-customizable whiteout format. So in particular, they do whiteouts differently than OCI does. So the way they do it is with a device node that's of major minor type 00, whereas the OCI spec says do it with this .wh prefix. And so if you generate an image like this, it's not exactly an OCI image because A, it's using Squashfest in the first place, but B, if you want to use Squashfest in this way, you have to use these device nodes instead of the whiteout prefixes. So that's sort of annoying, and that's hard-coded in the kernel, so it's difficult to change. So that's not awesome. This is a minor thing, but it doesn't support exactly one layer. So if you have a container with exactly one layer, you have to do some fiddling around with it in order to get it to work. So the tooling I've written does all that, but just it's a thing to remember. Yeah, and so this is relevant because base images have this format. There's also some issues with Squashfest. So when we're looking at playing around with this, the first thing is it's not really active, and the last commit in the kernel tree was from August of 2018. So people are not sending a lot of patches, and maybe that means it's done, but I don't think so because there's also really no user space libraries for generating blobs. In particular, the way that you generate a Squashfest is with this tool called Make Squashfest, and basically there's just a whole bunch of command line arguments you can pass this thing. So if you look in the code for what I've done to do this, we basically build up this massive command line argument of exclude these files but include these ones, so that we can generate exactly the layer diff that we want for a particular layer, which isn't really awesome. So it's kind of a brutal hack. So it doesn't support some file system primitives that containers use. The biggest one is ACLs. So for example, sometimes we use CentOS, and CentOS uses ACLs in various places so a classic example is ping. Ping needs to have cap net raw in order to be able to send the right kind of packets out. And everyone used to have it as setuid, and then there was all this discussion about why the hell do we have ping as setuid, so they started using ACLs and capabilities and stuff. So anyway, whatever, doesn't matter, it doesn't support ACL, that's sort of annoying. There are others, yeah, so there probably does need to be some work on Squashfest if we were to continue down this path. But we're doing this anyway, even though there are all these problems. And I guess one thing to say here is we're doing it kind of in the way I've described, which is sort of trying to thread all these hacks together, because we're really trying to see if this will work. This is one of these places where other people's input would be appreciated. I think I have a slide later, but there's some talk about an OCI v2 and what would that look like. I know there's been a lot of work in systemd in this tool called CA sync, which is content addressable sync, that addresses a lot of the deduplication issues, but doesn't necessarily address the sort of signing and auditing issues. So if you're interested in this sort of problem, come talk to me. We'd be interested in collaborating on potentially designing a new image format, or I don't know exactly what that looks like. But anyway, this is all size and sort of in the weeds, but one of the things that we're really interested in is updating containers, and sort of the original pitch of this talk is operator-centric way to update containers. So what does that look like? If you think of sort of the ways to implement containers as a spectrum, or implement I guess like code management as a spectrum. On one end of the spectrum, there's Docker or OCI images, which are bit for bit exactly what the developer built. You get exactly those same bits. So in particular, you get the same version of SSL, you get the same version of Python, you get the same version of Java, you get the same version of all the dependencies in the whole world that the developer used. So you know exactly that that's going to run. And that's very nice. But then you have all these problems where you have to go back hat in hand to the guy and ask him, can you build us another version with an updated dependency of SSL or whatever? Because while you got exactly the same bits that guy had, that means you have all the same bugs that he had, and there's software bugs and security stuff and whatever, so you got to patch stuff. And at the other end, there's traditional application packaging. So that's like if the way we used to do it, where you would build some container, or you would build some thing outside of a container, you would install it somehow, or you'd build a deb package or something. That deb package would list its dependencies. You get some version that isn't exactly the right match because whatever you were using on your local machine is different when you built the deb than the production environment, and so some little bug somewhere causes things to screw up, and that's annoying, and that's why we all switched to Docker in the first place. So this is a continuum, and I guess the insight here is that you probably want something in the middle. In particular, you may know that, okay, I really depend on this exact version of Python because, I don't know, the garbage collector has this particular behavior and we really care about that because we're a cool HFT firm and we care about things like that. So maybe you really know that Python's super important, but, if you're over here and you're talking about some library that nobody really, I don't know, isn't that important, or is mostly unused or whatever, or is like SSL, where there's maybe not a lot of functionality updates, but there's definitely some security updates. You don't necessarily care exactly what version of SSL you're using, you just want the latest one. So what you'd really like to do is, in some cases, you want to use the exact same version, and in other cases, you don't, and you want to use kind of whatever the latest is and allow people to kind of update it out from under you. And so one of the tools that I wrote is called Stacker, and it has this, it's sort of, you can think of it like Docker for the purposes of this, and this is sort of the basic format. I'm not going to explain a lot of it, but basically what you can see is there's two applications, A and B, and they both depend on OpenSSL and Python 3, and there's some, way that you install them. You clone the repo and you run some install script. But the first thing that you do is you yum install those two libraries. And so in this world, there's really not a great way to say, I'm going to rip this layer out and I'm going to stick this other one in. So when there is an OpenSSL bug, there's not a great way to say, oh, this is the layer that corresponds to the OpenSSL package. If I want to change the image as an operator, I can yoink out the SSL and stick in my new one that's patched. So you might imagine thinking about this problem slightly differently, in particular doing it like this. So, and the colors, I'm going to do some diagrams with the layers so the colors are relevant for that. So anyway, you might write your application install script like this, where on the left-hand side you have these two specifications for this is how to build something called SSL, this is how to build something called Python 3. And then on the right, you would say, start from this base, and then add this other thing that somebody built called SSL, and then add this third thing that somebody built called Python 3, and then install my application on top of that. And so what that looks like, so the SSL layer is built, the bottom two, say, are the CentOS base layer, and then the SSL layer is built on top. And then similarly, the Python 3 layer looks identical because it starts from the same CentOS base, but then we stick a Python layer on the top of there. And then this end result of our total build, so if you remember, there's the apply syntax, so we apply the SSL latest, we see that the bottom two layers are the same, so we just apply the layer that was different. Then we similarly apply the Python latest layer, the only layer that was different, and then we install our application on top. So we end up with something that looks like this, where the bottom was the base image. We have these two layers that we layered on top that were just the deltas for SSL and Python. And then we have the application delta on top. And the nice thing is then, if I want to do Python latest +1, all I do is the only thing I have to do is I change this one layer here, and then it's happy. And so that's the idea, is to build some tooling. And so we have some runtime tooling, but unfortunately it's not open source to do this. But anyway, that's the idea. And the last thing I'll just talk about is size. That was another complaint. And we basically punt on this. So we just didn't think about this, mostly because the provenance problems are more important to us. So yeah, this is my call to action. There's an issue about on some thing called an OCI implementation. There's some discussion on that thread. I guess there's some discussion on Twitter. I'm not a Twitter user, unfortunately, so I can't help you there. But I guess the question is, what would a new container image format look like? We're sort of doing this now because we're interested in it now, but I can imagine that we can solve both the size problem and the provenance problem if we come up with a clever solution. But we need help to come up with a clever solution, and that's where you come in. So thank you. If there's questions, I think I have like 3 minutes or something. One.
Hold on.
Yeah.
You did not open source this? What is the reason?
We have open sourced the tools for building it here. So there's two. The stacker is the tool to build images with this special apply syntax that I described, and then AtomFS is the file system to mount the OCI images as Squashfest. So that's part of the runtime, but we have a bunch of code that actually is built on top of this even, that also is not open source right now.
Okay, so one of the reasons that, not everywhere, but where that containers or this kind of things are used is for preserving software, which obviously if you start specifying your layer as latest means that chances are you will actually get something completely different if you try to rebuild your numerical computation platforms 5 years later. So have you thought about any way of, I don't know, specifying what it's like latest, but the preferred versions was something like that, or well, not sure, you really get what you mean.
Yes, so we mostly actually use semantic versioning for our layers. So and it functions exactly the same way you would think semantic versions function. And then if you want to, we don't actually do this now, but you could presumably do some globbing like fancy package managers like Cargo and the Go module system and stuff do, where they take the latest of some minor version. You could do a bunch of math there, but basically semantic version is the way we're handling it internally.
Other questions?
All right.
There's a couple here.
Thank you. I have a question. Did I understood correctly that stacker do something similar that section files from packaging do? So calculate paths which for files which should be a part of this layer.
It's possible. I don't actually know what section files do. So
just list the files or directories.
Yeah, I mean, exactly. So it's this idea of basically computing a binary diff over the layers, yeah. There's, I think, one more maybe.
Yeah, there was one more.
Yeah.
Is it possible to use Squashfest inside user namespaces?
I don't think so. I don't think it has FS user and S.
You can use Squash Fuse, but you need to use Fuse.
Yeah, so you can do it through Squash Fuse, but not Squashfest proper.
Yeah, that's what we do in Ubuntu and other distros. We run snaps now that are all Squashfest based, and we use Squash Fuse. That works pretty well.
Yeah, and like I say, Squashfest isn't really the greatest format, except for it's one that works for this use case right now, today, and we don't have to spend a lot of time inventing a new format. But if we're going to do all this other stuff, you know, implementing ideas from CA-Sync or whatever, potentially when we do that format, we could do something better, and also maybe make it safe for user namespaces. But yeah, come help.
Thank you.
Thanks.